At the end of the 19th century, humanity stood proudly at the summit of knowledge. The scientists of the age believed they had finally unlocked a universe. Newton's laws had tamed the planets, describing with elegant precision how the heavens moved. Maxwell's equations had united electricity and magnetism into one radiant theory of light. The steam engine had transformed industry, and the telegraph had conquered distance. In universities and lecture halls, professors told their students with calm confidence that physics was nearly complete, that all that remained were a few final details, mere refinements to polish an already perfect system. It was, they thought, the age of certainty, but in the shadows of that certainty, subtle cracks were beginning to appear, cracks that most ignored. The universe, it seemed, was not content to remain fully understood behind the smooth equations of classical mechanics. Something faintly rebellious stirred, small anomalies that refused to obey the old rules. Yet in 1890, no one suspected how deep those cracks ran. No one imagined that the very foundations of reality were trembling. In lecture rooms across Europe, professors spoke of energy as a continuous sea, something that could flow in infinite gradations. Matter was solid, predictable, governed by Newtonian determinism. Every cause produced a calculable effect. Every motion could be traced. Every outcome could be foreseen. It was a universe of order and logic, a clockwork cosmos wound by a divine hand and left to tick forever. Laplace, the great French mathematician, had even declared that if one could know the position and motion of every particle at one moment, one could predict the entire future and reconstruct the entire past. It was the ultimate dream of reason, perfect knowledge, perfect control. And yet, the dream was incomplete. Beneath the elegance of the equations lurked experiments that refused to fit. The spectrum of light emitted by heated objects, the mysterious blackbody radiation, mocked every law physicists tried to impose. The orbit of Mercury deviated slightly from Newton's predictions. And in laboratories, when light struck metals, strange electric currents were observed, phenomena no one could fully explain. But in that age of pride, scientists often brushed these mysteries aside, calling them minor irregularities. The great cathedral of physics, they thought, was nearly finished. The world of science in the 1890s was a world of great men. Lord Kelvin in Britain, Helmholtz and Boltzmann in Germany, Michelson and Morley in America, each building upon the magnificent structure of classical theory. Kelvin famously proclaimed that there is nothing new to be discovered in physics now. All that remains is more and more precise measurement. It was a statement that captured the arrogance and triumph of an era. The universe seemed conquered, its mysteries mapped, its laws eternal. But history, as always, was preparing a quiet surprise. In those days, light was understood as a wave, and heat as the agitation of molecules. The grand unification of matter and energy was thought to be complete, yet even the most confident physicists knew there were problems they could not solve. The equations describing how hot objects emit radiation led to absurd results. According to classical theory, a heated object should radiate infinite energy at short wavelengths, a catastrophe later mockingly called the ultraviolet catastrophe. It made no sense. But the community of scientists preferred to look away. How could a theory so powerful, so elegant, be wrong? Meanwhile, the Industrial Revolution had transformed Europe. Steam, electricity, and magnetism had turned into the engines of progress. Telegraph wires stretched across continents, and laboratories were temples of human ingenuity. Science had become a kind of faith, and physicists its high priests. To challenge the foundations of physics was almost heresy. And yet, in quiet corners of universities, a few minds began to whisper questions others dared not ask. In Munich, Berlin, Vienna, and Cambridge, a new generation of thinkers were born into this age of contradiction, an age where faith in reason was absolute, yet the mysteries of the universe deepened. The electron had just been discovered, hinting that atoms, once thought indivisible, were themselves worlds of motion and charge. Light, when examined more closely, behaved not always like a wave, but sometimes like a particle. The deeper scientists looked, the less certain they became, but they did not yet know that the man who would open the door to a new reality was already at work, quietly, methodically. unwillingly preparing the dawn of the quantum age. The late 19th century was a symphony of progress, but beneath its melody hummed a strange discord. Every new invention brought more questions. Every new precision revealed new uncertainty. The universe, it seemed, was teasing humanity, offering glimpses of something deeper, something invisible, something beyond the reach of Newton's clockwork. The most brilliant minds could measure heat, light, and energy with astonishing accuracy, yet they could not explain the simplest of nature's acts. Why does a heated object glow red, then orange, then white? Why do the stars shine as they do? Why is light itself divided into precise colors when passed through a prism? The answers lay just beyond the horizon, waiting for a mind willing to question the unquestionable. But in 1890, such a mind had yet to emerge. Max Planck was then a young German physicist, meticulous, conservative, and deeply devoted to the established laws of thermodynamics. He admired Newton and Helmholtz, and believed that science was a moral duty, a way to understand the divine order of nature. He was not a revolutionary, he was a perfectionist, a believer in the harmony of physical law. To him, the universe was not chaos, it was an orchestra conducted by reason, yet unknowingly, it was Planck who would one day shatter that harmony. The scientific world he inherited was built on the triumph of continuity. Everything in nature was thought to flow smoothly. Motion, energy, time, even existence itself. Between one moment and the next, there were infinite shades, infinite possibilities, infinite precision. The mathematics of calculus, the proud language of Newton, was founded on this idea of the continuous reality, it was said, had no gaps. Everything was connected by smooth transitions. And then came the light. The more physicists studied light, the stranger it became. When passed through narrow slits, it interfered with itself like a wave. When shone on certain metals, it kicked out electrons as if it were made of particles. It was both and neither. The world that seemed solid and predictable was beginning to flicker, but this was not yet Planck's concern. His world was that of heat, energy, and entropy, the grand laws of thermodynamics. Still, that one problem of blackbody radiation haunted him, as it haunted many others. Imagine a furnace glowing in a dark room. Its heat radiates outward, invisible at first, then red, then orange, then white as it grows hotter. Scientists could measure this radiation, but when they tried to calculate it from classical theory, their equations exploded into infinity. No matter how carefully they adjusted their assumptions, the math refused to behave. It was as if nature itself was defying logic. For years, no one could explain it. Lord Rayleigh, a giant of British science, tried to fit the data and failed. Wilhelm Wien, another great name, proposed formulas that worked at some temperatures but collapsed at others. Every attempt ended the same way: brilliance, then contradiction. It was a mystery that embarrassed the proud discipline of physics, but deeper than the embarrassment was the fear that something fundamental was missing, the same fear that haunted astronomers when they looked at Mercury's orbit and saw it deviate from Newton's predictions by a tiny but undeniable fraction. Fear that the laws which had built the modern world might not hold in the extremes, too small, too hot, too bright. The world before Planck was a world desperate for certainty. Science had given humanity the power to harness nature, but also a dangerous illusion that everything could be known, everything controlled. It was an age intoxicated by progress, where invention followed invention, and men dreamed of mastering even time and death. The microscope and the telescope had expanded human sight, yet they had also revealed deeper mysteries. At one end of scale lay the atom, invisible yet powerful. At the other, the cosmos, infinite and incomprehensible. And between them, the human mind stood trembling, confident, yet blind to what was coming. Max Planck would not come to revolutionize physics by choice, but by necessity. He was drawn into the blackbody problem, not because he sought fame or transformation, but because it was a question of harmony. Why did nature's music break at certain notes? Why did energy, the purest of quantities, refuse to behave continuously? For a man like Planck, who believed that the universe was guided by mathematical order, such dissonance was intolerable. He began to calculate, to test, to adjust formulas with the patience of a craftsman shaping marble. He did not know he was chiseling open the gateway to a new universe. But that is the irony of the time before him. The world thought it was reaching completion when in truth it stood at the brink of rebirth. The physicists of the 19th century were like sailors who believed they had mapped every ocean, unaware that the edge of the map led to an abyss that would swallow their certainty. They called it the classical age, and they thought it eternal. But in the small labs of Berlin and Munich, under the dim glow of gaslight, instruments flickered, readings wavered, and something in the data whispered that reality was not what it seemed. Energy, it appeared, did not flow like water. It leapt, like sparks, and in that leap, invisible and minute, the future of physics waited. The century was closing, but a new light was rising. The 19th century's last decade unfolded like the final act of a long and glorious symphony. Every note of classical physics still rang clear, but faint discord lingered beneath. In lecture halls, filled with chalk dust and quiet ambition, professors still spoke of Newton's perfection, of equations that bound the stars and ruled the tides. They believed that all mysteries were now a matter of precision, that the universe was a solved puzzle. But in laboratories where glowing filaments and mercury thermometers told subtler truths, nature whispered otherwise. It was not submission that she offered, but resistance. Something small, something unseen, defied the classical order. The light from a heated metal refused to follow the rules. The deeper they looked, the more reality slipped between their fingers. And amid this fragile calm, in Berlin, Max Planck was sharpening his mind against a problem most others had abandoned. He was a man of extraordinary discipline, the son of a theologian, raised on the belief that the world was governed by moral and mathematical order. He rose early, worked late, and lived quietly, more monk than celebrity. He did not chase novelty, he sought truth. To Planck, the universe was a cathedral of reason, and every equation was a hymn. Yet even his faith in logic was being tested. The problem of blackbody radiation, simple, stubborn, humiliating, refused to bow to the laws of classical physics. Planck did not yet know that this problem would transform him from a scholar into a prophet of a new reality. In those days, blackbody radiation was the scandal of science. A blackbody, a perfect absorber and emitter of energy, should, by all classical reasoning, release radiation smoothly across all wavelengths. But experiments showed something else. At low frequencies, the equations worked fine. At high frequencies, they exploded into nonsense. Energy predicted by the theory grew without limit, as if nature were bleeding infinite power into the ultraviolet spectrum. The data screamed for an answer, but none came. Even the greatest minds could only shrug. Some called it a technical error. Others quietly ignored it. To admit failure would be to question the very foundation of thermodynamics and electromagnetic theory. But Planck was not one to look away. He approached the puzzle as a craftsman approaches an imperfection in a finely made instrument, calmly, methodically, certain that there was harmony to be found. Late nights found him hunched over his desk. Under the dim light of a gas lamp, sheets of paper scattered like snow. He tried every mathematical trick he knew, bending classical formulas to fit the stubborn data. Again and again they refused. Desperation drove him to what he later called an act of desperation. He imagined energy not as a continuous stream, but as small, indivisible units, quanta. Each packet of energy would be proportional to the frequency of radiation, multiplied by a new constant, h, an unknown number that would come to bear his name. He did not believe it physically real. It was a mathematical fiction, a temporary scaffolding. Yet with this assumption, everything suddenly fit. The equations worked perfectly. The infinite energies vanished. Nature, it seemed, had been waiting for this key. When Planck presented his results to the German Physical Society in December 1900, few in the audience understood the magnitude of what they had just heard. It sounded technical, a small correction to an old formula. Planck himself treated it modestly, almost apologetically. He believed he had found a way to preserve classical order, not destroy it. But the universe had other plans. The introduction of h, Planck's constant, was the crack that would split the marble temple of classical physics. For the first time, energy was not continuous. It jumped. Reality, once thought to flow like a calm river, revealed itself as a sequence of leaps. each step discrete, each transition indivisible. The universe, at its most fundamental level, pulsed. Planck's discovery was both a triumph and a torment. He could not deny the success of his theory, but he resisted its meaning. He once confessed that he had been forced to accept the quanta against his will. He spent years trying to reconcile it with the smooth determinism of Newton and Maxwell, but the cracks only widened. Others, younger and bolder, took up the idea he had introduced and built upon it. Einstein used it to explain the photoelectric effect, revealing that light itself behaves as if made of particles. Bohr used it to describe the atom, explaining why electrons circle nuclei in fixed orbits. Heisenberg and Schrödinger would later weave it into the tapestry of quantum mechanics. But all of that lay ahead, in the world before Planck. The idea of a quantum was unthinkable, almost heretical. He was the bridge between two ages, the last classical physicist and the first quantum pioneer. The story of that bridge cannot be told without the world that came before it. For centuries, scientists had believed that the universe was predictable. Classical mechanics promised that if you knew where every particle was and how it moved, you could predict the entire future. It was a vision of a clockwork cosmos, perfect and eternal. That vision shaped not only science but philosophy, art, and religion. It gave comfort to the human mind, the illusion of certainty. But Planck's discovery tore that comfort away. It showed that, beneath the calm surface of reality, the universe danced in unpredictable steps. It was no longer a machine, it was a symphony, and each note played in quanta. Before Planck, the boundary between physics and metaphysics seemed clear. After him, it blurred. The old world of absolutes gave way to a realm of probabilities. Determinism cracked, and mystery returned to the heart of science. In time, this revolution would lead to the atom bomb, to lasers, to computers, to quantum entanglement and teleportation. But in 1900 it began with one man's uneasy compromise with nature. It began with Planck staring into the glow of a furnace and seeing, for the first time, that energy itself came in pieces. To grasp the courage of that moment, one must understand the intellectual climate of his time. Planck's Germany was steeped in the rationalist tradition. Philosophers like Kant and Leibniz had taught that nature was governed by reason alone, and Planck absorbed that faith. He saw science as a moral pursuit, an expression of divine order. The thought that the universe might be discontinuous, broken into quanta, felt to him like chaos. It was an affront to the idea of perfection. Yet his calculations would not lie. They whispered the truth. Energy does not flow, it leaps. And though he resisted, he listened. He once said, "A new scientific truth does not triumph by convincing its opponents, but because its opponents eventually die and a new generation grows up that is familiar with it." He had seen the birth of such truth, and he knew its price. The world before Planck was not a world of ignorance, it was a world too sure of itself. It believed that progress was infinite, that knowledge had an end, that reason alone could reveal the whole of existence. Planck's discovery broke that illusion. It reintroduced wonder into science. Not the naive wonder of superstition, but the awe of encountering a universe far stranger than imagination. The atom was no longer solid. Light was no longer simple. Time and energy, once continuous, were granular. Reality itself was woven from discrete pulses, each one a quantum heartbeat of the cosmos. If one could step back and look at history as a single film reel, the moment Planck wrote down his formula would be the frame where the world shifted focus, from the visible to the invisible, from certainty to curiosity. And though Planck's own voice was calm and measured, what echoed from that moment was thunder. It reached Einstein, Bohr, Dirac, Heisenberg, Feynman, all the minds that would build the quantum world. It changed how we see not only atoms, but ourselves. Before Planck, the scientist's goal was to define nature. After him, it became to interpret her. Where once laws were absolute, now probabilities reigned. The observer became part of the experiment. Reality was no longer a fixed stage. It was a living performance. That is the hidden legacy of the world before Planck. It prepared the mind of humanity for a leap it did not yet understand. And so, as the 20th century dawned, a quiet German professor closed his notebook. unaware that he had just rewritten reality. The gas lamps flickered. The laboratory fell silent. Outside, snow drifted over Berlin. The age of certainty had ended. The quantum century had begun. In hindsight, it is almost poetic. The man who sought order uncovered the foundation of uncertainty. The thinker who cherished continuity discovered the discreteness of existence. And the era that believed it had reached the end of science found, instead, its new beginning. The world before Planck was not destroyed by him. It was transformed. Its confidence gave birth to humility. Its clarity gave rise to mystery. From the ashes of determinism rose the strange, beautiful, unpredictable light of the quantum. Even today, every LED that glows, every GPS signal that guides, every microchip that computes, carries within it the echo of that moment in 1900. Planck's constant H hums silently at the core of our digital world, a number that defines the grain of reality itself. We live in a universe quantized by his discovery, a universe that flickers in steps too small to see but too powerful to ignore, and though the world before Planck is long gone, its spirit lingers in our search for meaning, in our balance between faith and reason, in our endless wonder at how the simplest questions still open the deepest mysteries. Because before Planck, physics sought to explain the universe. After him, it began to explore it. The light of that furnace in Berlin has never truly gone out. It burns still, in every photon, in every atom, in every spark of curiosity that drives us to ask, as he once did, what lies beyond the edge of certainty? It began not with thunder, but with a quiet equation, written in the dim light of a Berlin winter. Max Planck, meticulous and modest, did not set out to rewrite the universe. He was not a revolutionary. He was a man of reason, a seeker of harmony, a believer that nature obeyed elegant laws. To him, physics was the poetry of order, and yet it was this man, so careful, so disciplined, who would stumble upon the single idea that cracked the solid walls of classical science. His discovery, born of frustration and humility, would become the foundation upon which modern physics stands. It was unexpected, unwanted, and unstoppable. By the end of the 19th century, science stood tall, proud, almost arrogant in its achievements. The Industrial Revolution had transformed Europe into a machine of progress. Steam, electricity, and magnetism powered factories, cities, and communication across continents. The world seemed explainable, predictable, tamed by equations. Newton's mechanics described motion from cannonballs to planets. Maxwell's equations captured the dance of light and electromagnetism. Scientists spoke of universal laws with reverence, as if they were reading the very script of creation. And yet, beneath that triumph, there lay a small, unresolved question, the problem of blackbody radiation. In every laboratory of the era, the question haunted experimenters. When an object was heated, it glowed, first red, then orange, then white. The pattern of that glow, its distribution across different wavelengths of light, could be measured precisely. But when physicists tried to calculate it using the known laws, the equations failed. At long wavelengths, they predicted one thing, at short wavelengths, another, an impossible result known as the ultraviolet catastrophe. According to classical theory, a heated object should radiate infinite energy in the ultraviolet region, a prediction absurd enough to threaten the credibility of physics itself. For years, scientists tried to force the problem to obey the old laws. Lord Rayleigh and James Jeans developed equations that fit part of the spectrum, but not all. Wilhelm Wien proposed another formula that matched experiments at high frequencies but broke down at low ones. It was as if nature herself were mocking them, whispering a secret they were too proud to hear. Among those listening most intently was Max Planck. Planck had no desire to break the laws of physics. He wanted to save them. He believed deeply in the principle of continuity, that energy, like matter, could vary smoothly and infinitely. But the blackbody problem was a riddle that refused smooth answers. Every attempt to fit the data with continuous functions ended in failure. Planck's instincts told him that the answer lay not in abandoning classical theory, but in refining it. He began to treat the problem mathematically, experimenting with functions that could fit the observed curve of radiation intensity. On the evening of October 19, 1900, after weeks of calculation, Planck wrote down a formula that fit the experimental data perfectly. It was elegant, simple, and completely alien to everything known in physics. To make the math work, he had to assume that energy did not flow continuously but came in discrete packets, each proportional to the frequency of light. The proportionality constant he introduced, a tiny number he called h, was something new, something fundamental. It would later be known as Planck's constant. At first, he treated it as a mathematical trick, a clever fix, not a real description of nature. But nature would not allow it to remain a trick. When Planck presented his results to the German Physical Society in December 1900, he described them with modesty, even hesitation. Few in the audience realized they were witnessing the birth of quantum theory. The world of physics had just changed forever, though it would take decades for anyone to grasp how deeply. Planck's formula matched reality with uncanny precision, but it did so by breaking the sacred rule of continuity. It declared that at the smallest scales, energy came in lumps, quanta, rather than smooth flows. It was a revelation so strange, so subtle, that even Planck himself did not yet believe it. In private, Planck struggled to reconcile what he had found. How could energy, the most fundamental property of the universe, be discontinuous? It violated everything he had been taught, everything he believed. He called his step an act of desperation, born not of ambition, but of the stubborn refusal of nature to yield to old logic. He tried to interpret his constant as a mathematical artifact, not a physical truth. But as more experiments confirmed the accuracy of his law, doubt became impossible to escape. What had started as a patch on a broken theory was turning into a doorway to a new world. The more Planck examined the implications of his formula, the more he realized that he had uncovered something deeper than he intended. The quantization of energy meant that the universe was not continuous after all. It was granular, divided into indivisible packets. The smooth waves of light were, at their core, made of tiny bursts of energy. This was not merely a refinement of physics, it was a redefinition of reality. Still, Planck resisted the notion. He was a conservative man, not a dreamer. He distrusted the growing voices of radical thinkers who sought to overturn classical physics. Yet, his own work had given them the ammunition they needed. When a young Albert Einstein applied Planck's quantum idea to light in 1905, suggesting that light itself was composed of quanta, later called photons, the revolution became unstoppable. Planck's reluctant constant had set the world of physics ablaze. To understand why Planck's discovery was so shocking, one must imagine how the scientific mind of the 19th century viewed reality. Everything was governed by determinism, the belief that every event was the direct result of a previous cause, perfectly calculable in principle. If one knew all the forces and positions of particles at any given time, the entire future of the universe could, in theory, be predicted. This was Laplace's dream. The clockwork cosmos wound up and running by immutable law. Planck's quantum hypothesis shattered that dream. By introducing discreteness into energy, Planck had implicitly introduced uncertainty. If energy could only change in steps, then transitions between states were not continuous but abrupt, probabilistic. It was a small crack, but from it grew the vast landscape of quantum mechanics, a world of probability, duality, and paradox. The physics of Newton and Maxwell described the macroscopic universe, the falling apple, the orbiting moon, the swing of a pendulum. Planck's discovery opened the microscopic world, the realm of atoms, electrons, and photons, where certainty dissolves into chance. It is difficult today to grasp the magnitude of that leap, because we live in the world it created. Every smartphone, every computer, every laser, every MRI machine, every solar panel, every LED, all rely on the principles that descend from Planck's constant: the structure of matter, the behavior of light, the chemistry of atoms, the fusion inside stars. All of it flows from that single idea. Energy is quantized, yet at the moment of its birth, it seemed trivial, even accidental. Planck himself described the period after his discovery as a time of inner conflict. He could not abandon the classical worldview that had guided him all his life. His mind, disciplined by years of thermodynamic study, resisted the notion that nature could be discontinuous. He tried, again and again, to derive his formula without quanta, to return to the smooth universe of old. Each attempt failed, the data would not bend, nature had spoken, and Planck had no choice but to listen. His constant, h, was unimaginably small, 6.6262610, 34 joule-seconds. It seemed insignificant, irrelevant at human scales. But it was the measure of the universe's granularity, the dividing line between the classical and the quantum worlds. Above it, the laws of Newton still ruled. Below it, reality danced to a different rhythm. In that rhythm lay the foundations of the 20th century's greatest scientific revolutions: relativity, quantum mechanics, atomic theory, and beyond. And yet, what made Planck's discovery so extraordinary was not just its implications, but its origin. It was not the product of wild imagination or bold rebellion. It was born of patience, humility, and precision. Planck was not trying to change science, he was trying to preserve it. But in his devotion to truth, he stumbled upon the invisible fault line that separated two eras. The story of that discovery is not the story of a sudden flash of genius, but of endurance. For years, Planck studied entropy, radiation, and the statistical laws of thermodynamics. He was fascinated by the work of Ludwig Boltzmann, who argued that entropy, the measure of disorder, was rooted in probability. Planck admired Boltzmann but disagreed with his interpretation. He wanted a deterministic foundation for thermodynamics, not a statistical one. Ironically, it was through the very problem he resisted that he would discover the quantum. When Boltzmann died in 1906, exhausted and unrecognized, Planck mourned him deeply, realizing at last that Boltzmann's probabilistic view of nature had pointed toward a truth larger than either of them could have foreseen. Planck's journey was as much philosophical as scientific. He once wrote, "Science cannot solve the ultimate mystery of nature, because we ourselves are part of that mystery." His discovery forced him to confront the limits of human understanding. The world he had known, a world of continuity and certainty, was giving way to one ruled by discontinuity and doubt. But from that doubt emerged a new kind of beauty, a universe far more intricate, subtle, and alive than the clockwork of Newton at the turn of the century. As Berlin's streets filled with the light of new electric lamps, Planck's constant began its invisible work. It lay hidden in every photon that streamed from those bulbs, in every atom that vibrated in the metal filaments. The age of classical certainty had given birth to the age of the quantum, and though Planck himself did not live to see all its consequences, he had set into motion the greatest transformation in the history of science: the realization that reality is not smooth, but quantized, not continuous, but built of leaps. The discovery that changed science forever began as an act of faith and reason, but it ended as a lesson in humility. Planck's constant, small beyond comprehension, carried within it the blueprint of a universe that defied intuition. It taught humanity that truth does not always align with expectation, that even the most precise equations can conceal mysteries deeper than imagination. By the time Planck realized the full meaning of his formula, the world around him was already beginning to shift. Einstein, Bohr, and others would carry the torch he had lit, each pushing the boundaries of the quantum world further, revealing that uncertainty was not an error but a law of nature. The solid universe of the 19th century dissolved into a shimmering web of probabilities. And at its center, quietly glowing, remained Planck's constant, the fingerprint of the revolution that began when one man refused to ignore a problem no one else could solve. In the months following his presentation to the German Physical Society, Max Planck felt a strange disquiet within himself. His equation worked perfectly, yet it defied the world he thought he understood. He had long believed that nature was a grand continuum, a flawless flow of cause and effect like the graceful arcs of planetary motion. But now, his own discovery whispered that nature was not smooth but granular. It was as if he had peeled back the surface of reality and seen it flicker on and off in pulses too small to imagine. He found himself revisiting his own formula late into the night, his pen gliding carefully over sheets of paper already filled with equations. He kept asking the same question: what does it mean? Was this quantization real, or just a mathematical convenience? Had he revealed a hidden truth about the universe, or had he merely constructed a clever fiction to make the numbers fit? The more he tried to explain it away, the more the evidence pressed upon him. Nature, indifferent to his discomfort, continued to behave as if energy truly came in discrete packets. Planck's discovery did not explode across the scientific world overnight. The early 1900s were not yet ready to accept that reality itself could be built from leaps rather than flows. His formula was acknowledged, admired for its precision, but its philosophical implications were largely ignored. The community saw it as a useful fix, not a revolution. Yet beneath the calm surface of academia, the seeds of a new era had been planted. 5 years later, in 1905, a 26-year-old patent clerk in Bern named Albert Einstein read Planck's papers and saw what others did not. To him, Planck's quantum hypothesis was not just a mathematical trick, it was the key to understanding light itself. In his paper on the photoelectric effect, Einstein proposed that light was made of particles, quanta of energy, later called photons. It was a bold and dangerous claim. It meant that light, the very essence of waves, could also behave as a stream of discrete energy packets. It defied common sense, yet it explained experiments that no one else could. Einstein had taken Planck's reluctant idea and turned it into a weapon against the old physics. When Planck read Einstein's work, he was both fascinated and uneasy. He admired Einstein's brilliance, but he hesitated to accept such a radical interpretation. Still, he recognized that Einstein's explanation of the photoelectric effect fit beautifully with his own radiation law. Together, their ideas formed the first stones of what would become quantum theory. What made this discovery so extraordinary was not only that it worked, it was how deeply it changed humanity's perception of reality. Until then, physics had been a story of clarity, of solid truths and unbroken laws. Now it became a story of paradox. Light was both a wave and a particle. Matter could behave as both solid and fluid. The universe, once thought to be precise and predictable, became probabilistic and uncertain. It is easy now, from the vantage point of the modern world, to underestimate how shocking this was. Imagine living in a time when the very word atom meant indivisible solidity, then learning that even those atoms danced to rules stranger than imagination. Planck's constant, that tiny number buried in his equations, was like a key to an invisible kingdom, a kingdom where the rules of ordinary logic did not apply. It measured the smallest possible action in the universe, a kind of cosmic pixel defining the granularity of existence. Everything below that scale, every photon, every electron, every vibration of an atom, was governed by the quantum. The implications spread slowly at first, like ripples across still water. Niels Bohr used Planck's constant to explain the structure of the atom in 1913, showing that electrons could orbit only at specific energy levels. When they jumped between these levels, they emitted or absorbed quanta of light, precise packets of energy described by Planck's formula. It was the first time the quantum idea was applied to the building blocks of matter itself. Bohr's atomic model worked because Planck's constant defined the size of those energy jumps. Without it, the atom would collapse into chaos. The revolution Planck had begun, almost unwillingly, now had momentum. Across Europe, physicists wrestled with the strange new world of the quantum. Some resisted it fiercely. Others, like Bohr, embraced it as a revelation. Werner Heisenberg would later strip away the last remnants of classical certainty by introducing the principle of uncertainty, declaring that one could never know both the position and momentum of a particle precisely. Erwin Schrödinger countered with his wave equations, describing how matter behaved like a wave of probability. These ideas, though born decades later, all traced their lineage back to Planck's constant, back to that quiet winter in Berlin when a reluctant physicist dared to divide energy into steps. And yet, throughout all of it, Planck himself remained humble, even skeptical. He once said, I cannot understand how anyone can deny the continuity of nature. He viewed his quantum hypothesis as a temporary bridge, not a final truth, but the world had already crossed that bridge. His discovery had taken on a life of its own, shaping not only physics, but philosophy, art, and technology. It is impossible to overstate how much the quantum changed human thought. Before Planck, the universe was mechanical. After him, it was mysterious. The classical world of certainty gave way to a quantum world of probabilities. The laws that once seemed eternal were revealed to be approximations, valid only at large scales. Beneath them lay a deeper, more delicate order, one that pulsed in rhythm with Planck's constant. That rhythm now beats at the heart of everything we do, the transistor that powers your computer, the laser that reads your DVDs, the LED that lights your room, all owe their existence to the quantization of energy. Planck's discovery made possible the entire digital age. Each bit of information in a computer, each photon in a fiber optic cable, each quantum dot in a display, all are echoes of that original realization. That energy comes in quanta. And yet, when one looks back at Planck himself, it is not ambition one finds, but serenity. He was not a man intoxicated by fame or revolution. He was a man of patience, whose greatest gift was his refusal to look away from truth. He once said, "It is not the possession of truth, but the pursuit of it, that ennobles the scientist." His discovery came not from desire to disrupt, but from the courage to persist where others had surrendered. That persistence changed everything. The true beauty of Planck's discovery lies not only in what it explained, but in what it revealed, that the universe is both knowable and forever mysterious. Each answer births new questions. Each equation opens new abysses. Planck's constant became a symbol of that eternal dance between knowledge and wonder. Even in his later years, when he had won the Nobel Prize and his name had become legend, Planck remained introspective. He often spoke of the moral dimension of science, of how discovery demanded humility. Science, he said, progresses funeral by funeral. He had lived long enough to see his once controversial idea become the foundation of a new world view, but he never forgot the quiet struggle that had birthed it. His personal life was marked by tragedy. Wars that tore through his homeland, the loss of his sons, the collapse of the world he had known. Yet through it all he held on to one belief, that the search for truth was sacred. He saw in nature not chaos but divine order, an order that, though hidden, could be glimpsed through mathematics. His constant, he believed, was not an accident, but a clue left by the Creator in the machinery of existence. And so, when historians speak of Planck's unexpected discovery, they mean more than a scientific formula. They speak of a moment when humanity glimpsed a deeper layer of reality, when the curtain of the universe fluttered for an instant, and we saw that beneath the continuous world of our senses lies a quantum heartbeat. His constant, small, silent, absolute, measures the scale at which existence itself becomes granular. It is the dividing line between the predictable and the mysterious, between the world we see and the one we cannot. Every time a photon of light travels across space, every time an electron jumps within an atom, every time energy changes form, Planck's constant governs that act. It is the cosmic rhythm that underlies all motion, all heat, all life, and though we rarely think of it, it defines the limits of what can be known. There is a smallest possible step in energy, a smallest possible action, a smallest whisper of existence, and it bears Planck's name. He did not seek to be remembered as a revolutionary. He saw himself as a craftsman of theory, a servant of truth. But in the quiet simplicity of his equation, he redefined the possible. He showed that the greatest revolutions do not always begin with rebellion. They sometimes begin with obedience. Obedience to the stubborn facts of nature. Obedience to the quiet voice that says, "This cannot be ignored." And that is the essence of Planck's discovery. It was not born of chaos, but of clarity. It was the universe revealing, through one man's persistence, that even the laws of nature have deeper layers yet unseen. It was the moment when physics turned its gaze inward, from the grand motions of planets to the invisible dance of atoms, and realized that beneath every certainty lies a field of probabilities. Planck's unexpected discovery did more than change science. It changed the way humanity perceives existence itself. It replaced arrogance with awe, finality with curiosity, and replaced the notion of a mechanical cosmos with a living, vibrating quantum reality. The world he left behind could never again pretend to be simple. And so the story ends as it began, in quiet reflection, a professor in Berlin, closing his notebook after a long day, unaware that he has rewritten the story of reality. Outside, the snow still falls, the gas lamps burn softly, the equations rest on his desk, their ink barely dry. Somewhere within those lines of symbols lies the constant H, the smallest whisper of the universe. It would take generations for others to hear it clearly, but when they did, the universe itself would seem to speak. That reality is not a smooth melody, but a symphony of quanta, and that one man, in a moment of humble desperation, had struck the first note. At the turn of the 20th century, the world of science stood upon the edge of certainty and chaos. The old order still reigned. Newton's clockwork universe, Maxwell's waves of light, the unshakable confidence that every question could be answered by mathematics and reason. The great minds of Europe believed they were closing the final pages of physics. Everything, they thought, was known except for a few small clouds on the horizon, as Lord Kelvin famously said. But in those clouds, storms were gathering. Within them, something unseen was forming. A revolution that would not roar with the arrogance of conquest but whisper through the trembling hand of a quiet German physicist who had no desire to change the world. It was a revolution born not of ambition but of desperation. Max Planck was not a man of rebellion. He was a man of discipline, order, and faith. Born in 1858 in Kiel, Germany, he grew up in a family of scholars and theologians who taught him that truth was sacred and that science was not a weapon to disrupt but a lens to understand the divine harmony of creation. In an age of romantic speculation, Planck stood apart, precise, logical, reserved. He did not chase glory. He sought understanding. His world was built upon the certainty of laws, energy conserved, motion predictable, nature obedient to reason. But nature, as always, had secrets. When Planck began his studies in thermodynamics and radiation, physics seemed a temple of perfection. The equations of heat and light had long been written. Yet there was one question that refused to submit: the problem of blackbody radiation. Every object that absorbs all light that falls upon it, a so-called blackbody, also emits light when heated. At first, this light glows red, then orange, then white, as the temperature increases. Physicists had measured its intensity across wavelengths with precision, but no theory could explain it. Classical physics predicted that as frequency increased, the energy radiated should grow without limit, a result so absurd that it implied a hot object would emit infinite energy. This catastrophe was not just mathematical, it was philosophical. It meant that the proud architecture of classical physics could no longer describe reality. Planck approached the problem not as a revolutionary, but as a craftsman. He believed that truth could be extracted from patience and logic, not chaos. For 6 years, he wrestled with the equations, refusing to accept that the laws of thermodynamics and electromagnetism could fail. Every morning he returned to his desk with meticulous resolve, recalculating constants, revising formulas, comparing them to the data from experiments performed by Heinrich Rubens and Ferdinand Kerlbaum, but the curve of radiation intensity would not yield. At low frequencies, one set of equations fit perfectly. At high frequencies, they failed completely. It was as if nature had drawn a veil at the smallest scales, a veil no equation could pierce. By the autumn of 1900, Planck was exhausted. His mind, sharpened by reason, began to consider what he had always resisted. Perhaps energy itself was not continuous. Perhaps at the smallest scales, nature behaved in steps, not flows. He resisted the thought. It contradicted every principle he believed in. Energy, like time, had always been considered smooth, divisible without end. But the data demanded something different. In a moment of reluctant brilliance, Planck proposed a daring idea. What if the exchange of energy between matter and radiation occurred not continuously, but in discrete packets? He wrote it simply, almost timidly, as a mathematical necessity. E equal to et nu, energy equals a constant times frequency. The constant h was unimaginably small, 6.626x10, 34 joule seconds, a number that seemed trivial, irrelevant to the grand scales of the cosmos. But that number, that constant, was the first measure of the quantum. It was the invisible rhythm by which the universe pulsed. Planck did not yet realize what he had done. He thought it was a temporary fix, a mathematical trick to make the formulas behave. But nature was speaking through him, and her voice was absolute. When he presented his findings to the German Physical Society on December 14, 1900, the room was quiet. The presentation was brief, almost uneventful. There were no fireworks, no gasps of astonishment. Planck's words were cautious, technical, stripped of emotion. He believed he had merely solved a small theoretical issue. No one in that hall, not even Planck himself, understood that a new era had begun. It was the birth of the quantum, the dawn of a physics that would redefine reality itself. But revolutions rarely announce themselves with drums and banners. They begin in silence, in the quiet defiance of a single mind refusing to ignore what it sees. For Planck, it was not a triumph, it was a surrender. He had been forced to abandon the very idea of continuity that had defined physics for centuries. He called it, humbly, an act of desperation. In his diary, he confessed that he did not believe energy quanta were real, they were a convenient fiction. But nature, indifferent to belief, would prove him wrong. Within 5 years, Einstein would use Planck's constant to explain the photoelectric effect, showing that light itself behaves as if made of particles, quanta of energy that can knock electrons from metal surfaces. It was the first true confirmation that Planck's desperate assumption described reality. What began as mathematical necessity had revealed a hidden truth. The universe, at its most fundamental level, was not continuous but quantized. Energy did not flow, it leapt. Light was not just a wave, it was also a particle. This realization shattered the illusion of certainty. For centuries, scientists had believed that if you knew the position and motion of every object, you could predict the future with perfect precision. The universe was thought to be deterministic, like a vast clock ticking according to fixed laws. But Planck's discovery cracked that clock open. It revealed a universe built from probabilities, where the smallest events could not be predicted but only described by chance. Planck did not welcome this new world. He was a man of moral order, not cosmic chaos. He believed deeply in the unity of science and faith, in a world guided by divine reason. The idea that nature could be discontinuous, that energy could appear and disappear in sudden jumps, unsettled him profoundly. He spent years trying to reconcile his formula with the continuous laws of thermodynamics, but the deeper he went, the more the evidence contradicted his hopes. Reality had chosen its path, and it was quantum. And yet, it was precisely this conflict, his refusal to give up, his desperation to preserve harmony, that gave birth to the revolution. It was not the arrogance of a radical mind, but the humility of a devoted one that transformed physics. Planck's act of desperation was, in truth, an act of devotion to truth itself. His faith in reason did not lead him to stability, it led him to revelation. As the years passed, the implications of his discovery began to unfold like the petals of an infinite flower. Niels Bohr used Planck's constant to describe the structure of the atom, proposing that electrons could orbit only at specific energy levels. Discrete steps defined by H. Louis de Broglie extended the concept, suggesting that particles themselves have wavelengths, that matter could behave like waves. Schrödinger and Heisenberg would later formalize it into the equations of quantum mechanics, turning Planck's hesitant step into a fully fledged theory. Every advance, every new discovery, traced its lineage back to that night in 1900, when Planck, driven by despair, divided energy into quanta. It was as if he had thrown a stone into the still waters of physics, and its ripples had reshaped the universe. His constant, h, became the most important number in science, appearing in every equation that described the microcosm of atoms and light. It defined the limits of certainty, the boundaries of the knowable. In the decades that followed, the quantum revolution would change everything. technology, philosophy, even the way humans understood themselves, but at its heart, it remained what it had always been, a story of desperation turned into discovery. Planck's struggle to make sense of the blackbody problem was not the pursuit of fame, it was a man wrestling with the silence of the unknown. He was a craftsman trying to repair a crack in the wall, only to realize he had opened a doorway to another world. The most remarkable part of the story is how ordinary it seemed at first. There were no grand declarations, no manifestos of revolution. The birth of the quantum was as quiet as the ticking of a clock. But beneath that calm, the universe had changed its language. No longer could energy, matter, and light be described as continuous symphonies. They were quantized notes, discrete vibrations playing in cosmic rhythm. The melody of nature had been rewritten, and humanity was just beginning to hear its new tune. As Planck continued his work, he began to sense that he had unleashed something far beyond his control. He once wrote, "A new scientific truth does not triumph by convincing its opponents, but because its opponents eventually die." He knew that his discovery would take time to be understood, perhaps generations. But he also knew that truth, once revealed, cannot be hidden again. The quantum had been born, and it would grow, evolve, and transform everything that came after. The birth of the quantum was not just a scientific event, it was a philosophical awakening. It reminded humanity that certainty is an illusion, that even the most perfect theories crumble before nature's complexity. It humbled reason, not by destroying it, but by expanding it. For Planck, the revelation was both exhilarating and painful. He had looked into the machinery of the universe and found not a clock, but a dance. Chaotic, rhythmic, mysterious. He had sought stability and found motion. He had sought order and found wonder. The revolution he began was not loud, but it was eternal. From his act of desperation came a truth that reshaped not only physics, but the very idea of reality. The winter of 1900 faded into history quietly. Snow melted from the streets of Berlin, the gas lamps flickered out one by one, and life moved on. To most of the world, nothing extraordinary had happened, yet within the cramped lecture room where Max Planck had presented his findings, something had indeed shifted. The ground beneath science itself had begun to tremble. For centuries, physicists had walked confidently upon the foundation of continuity, but now that foundation had cracked. No one knew it yet, not even Planck himself, but the world had crossed a line from which there would be no return. Planck's idea, that energy could exist only in discrete packets, was not greeted with excitement, it was treated with polite confusion. Most scientists viewed it as a mathematical device, a temporary adjustment to make the equations fit. The thought that it might represent a real property of nature seemed absurd, but time has a way of revealing what the present cannot see. The seed that Planck planted out of desperation would, in the years to come, grow into a towering tree of discovery, its roots reaching into every corner of science and philosophy. The early 1900s were years of transition. The Industrial Revolution had made physics practical. Planck's discovery would make it profound. Yet Planck himself remained cautious, almost reluctant to claim victory. He continued refining his equations, trying to derive them from classical principles, hoping to find a path back to continuity. But nature, once unveiled, would not return to its disguise. The more experiments were performed, the more evidence piled up in favor of the quantum. Then came 1905, the miracle year. A young Albert Einstein, unknown to most of the scientific establishment, took Planck's hesitant constant and applied it boldly. He proposed that light itself was quantized, made of packets of energy, photons, that could knock electrons out of metal surfaces. This photoelectric effect, which had puzzled physicists for years, now made perfect sense. Einstein had not only accepted Planck's idea but expanded it into a principle of nature. What Planck had introduced as a desperate fix, Einstein embraced as truth. Planck, ever the cautious mind, struggled to follow. He admired Einstein's insight, but part of him resisted its implications. Light, in his understanding, was a wave, a continuous oscillation described perfectly by Maxwell's equations. To think of it as a particle was to undo decades of certainty, but evidence speaks louder than belief, and Einstein's theory matched experiment after experiment. Slowly, reluctantly, Planck began to see that his constant h had uncovered something deeper than he had imagined. It was not a mathematical convenience. It was the fingerprint of the universe itself. The revolution, however, was not quick. The physics community moved like a glacier, slow and skeptical. For years, the old and new worlds coexisted uneasily. Classical physics continued to explain the motion of planets and machines, while quantum physics began to describe the behavior of atoms and light. Two realities existed side by side, one smooth and predictable, the other fragmented and mysterious. It was as though humanity had discovered that the universe spoke in two dialects, one we could hear and one we could barely understand. In the following decades, that second dialect became the language of the future. Niels Bohr, a Danish physicist, built upon Planck's constant to explain the structure of the atom. He proposed that electrons did not orbit the nucleus freely, but jumped between discrete energy levels, emitting or absorbing light in quanta defined by H. Bohr's model matched experimental data perfectly. And for the first time, the quantum seemed not just plausible but real. Yet the more scientists explored this new world, the stranger it became. Matter behaved like waves. Waves behaved like particles. Cause and effect blurred. Werner Heisenberg discovered that it was impossible to measure both the position and momentum of a particle precisely. The more one knew of one, the less one could know of the other. Schrödinger, seeking to understand this paradox, described particles as wave functions, mathematical clouds of probability. The universe, once thought to be a clockwork mechanism, now appeared to be a shimmering field of possibilities. Planck watched this revolution unfold with both pride and discomfort. He admired the brilliance of the younger generation, but he felt alienated by their philosophical boldness. For him, the quantum was a necessity, not a creed. He accepted that energy was quantized, but he refused to abandon the idea that behind it all, nature remained continuous and rational. Still, he could not deny that the world had changed. His act of desperation had unleashed an idea that no one could control. The quantum revolution soon leaped beyond theory. As the 20th century progressed, technology began to catch up with theory. Quantum mechanics explained the behavior of semiconductors, the materials that would become the foundation of electronics. It revealed the mechanism behind chemical bonds, nuclear reactions, and even the life processes within cells. The quiet constant that Planck had introduced to save a broken formula now governed the functioning of everything, from lasers to computers to MRI machines. It is one of history's greatest ironies that Planck, the man who sought harmony, gave birth to the science of uncertainty. The revolution that grew from his work was one he never intended. But that is often the way of truth. It arrives not through ambition but through surrender. When the familiar fails, the mind must let go. And in that letting go, it glimpses something new. By the time Planck received the Nobel Prize in Physics in 1918, his quantum hypothesis had matured into the foundation of modern physics. He was honored for his discovery of energy quanta, though he continued to call it a hypothesis. In his acceptance speech, he spoke not of glory, but of perseverance. The pioneer must be content if, by his work, he has smoothed the way for those who come after him. He saw himself not as a prophet of a new age, but as a craftsman who had uncovered a hidden pattern. Yet that pattern, the quantization of energy, had rewritten the book of nature. What makes this story extraordinary is how human it is. The birth of the quantum was not born of genius alone, but of humility. It was the result of a man who refused to lie to himself, who dared to say, "The old laws do not fit. Something new must be true." It was the courage to accept failure, to see beauty in chaos, to trust mathematics even when it contradicted intuition. In that courage lies the soul of science. The philosophical impact of Planck's discovery extended far beyond laboratories. It challenged the very meaning of reality. If energy could exist only in jumps, what did that say about time and motion? If matter behaved as both wave and particle, what did that mean for the nature of existence itself? The old dream of determinism, the belief that the universe was predictable in every detail, began to fade. In its place grew a new understanding, that the universe is not a fixed script but an unfolding story, written one quantum at a time, And at the heart of that story, silently governing every act of creation and destruction, lies Planck's constant. It defines the smallest possible unit of action, the boundary between the classical and quantum realms. It is the number that tells us how the universe dances, the rhythm of its smallest steps. Without it, stars would not shine, atoms would not exist, and light itself would lose its form. As Planck aged, he came to see that his act of desperation had been something greater, a revelation of nature's depth. He accepted, finally, that the discontinuity he had resisted was not chaos but order of another kind. The quantum world, strange as it seemed, was not broken. It was complete in its own mysterious harmony. He often compared science to a great cathedral built over centuries, each generation laying a few more stones upon the foundation. His stone, he knew, was unlike any before it. It marked the transition from certainty to wonder. His later years were darkened by tragedy. The devastation of 2 world wars, the death of his children, the collapse of his country. Yet even as the world around him crumbled, Planck held fast to his faith in the unity of creation. He saw no conflict between science and spirituality. To him, the quantum was not proof of chaos, but of divine order beyond human comprehension. The scientist, he once said, is a man who never stops asking questions, and the greatest of those questions, he believed, led not away from faith, but deeper into it. When Max Planck died in 1947, the world he had helped create was unrecognizable. Quantum mechanics had become the foundation of physics. Einstein's relativity had joined it to form the twin pillars of modern science. Nuclear energy, quantum chemistry, and solid-state physics had all arisen from the constant he had discovered half a century earlier. The revolution born of his desperation had become the defining language of the 20th century. Today, we live surrounded by the legacy of that revolution. Every digital screen, every medical scan, every beam of laser light carries within it the whisper of Planck's constant. Quantum mechanics has given us transistors, quantum computers, cryptography, and the deepest understanding of matter ever achieved. Yet even now, its mysteries remain. The more we learn, the stranger it becomes. Reality, at its core, is not made of solid objects, but of probabilities, vibrations, and fields of energy that flicker in and out of existence, according to quantum rules. It all began with a man who did not seek to change the world, who, in his own words, acted against his will. The birth of the quantum was not a conquest. It was a confession that the universe was more complex than even the greatest minds could imagine. In the silence of his study, Planck had listened closely to nature, and in that silence he heard the pulse of the cosmos, a rhythm that would echo through every discovery to come. More than a century later, his act of desperation stands as a testament to humility. It reminds us that science, at its best, is not the pursuit of certainty, but the courage to dwell in uncertainty. The quantum was born not from arrogance, but from the willingness to admit, I do not know, and therefore I must ask. The night he first wrote down his equation, Planck closed his notebook and set down his pen, unaware that he had rewritten the story of existence. The lamplight flickered, the air outside was cold, and the snow fell silently on Berlin. He had not discovered a new law, he had revealed a new reality, a universe not of endless continuity but of countless moments, a universe where even the smallest act is sacred, where every leap of energy carries the signature of creation. And so the quantum was born, not from ambition, but from the quiet desperation of a man who refused to stop seeking truth. How Planck's constant became the key that unlocked modern physics marks the moment when a simple symbol, h, transformed from a mathematical patch into one of the most profound discoveries in human history. In the beginning it appeared as a small detail in an obscure paper, a number so tiny that no one could imagine it held the blueprint of the universe. But within that constant lay the secret rhythm of reality, the boundary between what could be known and what could only be imagined. Planck's constant did not merely describe a physical property, it revealed that nature itself operates in notes, not in continuous sound. It was the key that opened the locked door between the world of the visible and the invisible, between the deterministic past and the quantum future. When Planck first wrote his equation, he did not think of h as revolutionary. It was simply a constant required to make the mathematics fit the data of blackbody radiation. Its value, 6.626x10, 34 joule-seconds, seemed almost laughably small, far removed from anything a human being could touch or measure. Yet that number became the cornerstone of modern physics. It defined the scale at which the classical laws of Newton and Maxwell dissolved, and a new landscape began. It told scientists where the smooth fabric of nature gave way to the grain of reality, like a painting that, when examined closely enough, reveals its individual strokes. The power of H lay not in its size, but in its meaning. It meant that energy could no longer be divided infinitely. It existed in packets, quanta, each one carrying an amount of energy proportional to its frequency. That simple idea became the foundation of quantum mechanics, shaping the theories of Einstein, Bohr, Schrödinger, and Heisenberg. Einstein used H to explain how light behaves both as a wave and a particle. Bohr used it to describe the quantized orbits of electrons within atoms. Schrödinger built it into his wave equations, and Heisenberg discovered that it set a fundamental limit to what could be known. The uncertainty principle, which states that one cannot simultaneously know both the position and momentum of a particle beyond a certain precision, a limit governed by Planck's constant itself. Through H, the universe revealed its smallest heartbeat. It dictated how energy transitions between atomic states, how photons are emitted, how electrons move. Every quantum leap, every flash of light, every vibration of an atom is governed by this constant. It became the silent law of the microscopic world, invisible yet omnipresent. The same constant that determines the color of light from a star also determines the flow of electrons in a microchip. Across scales, from the heart of an atom to the fabric of space-time, H connects everything. But what made Planck's constant truly world-changing was not just its use in physics, it was what it taught humanity about knowledge itself. It shattered the dream of absolute determinism. Before H, scientists believed that with enough information, the future could be predicted perfectly. Planck's discovery showed that nature does not reveal all her cards. At the smallest levels, reality becomes statistical, probabilistic, uncertain. The laws of physics no longer promised exact predictions, but probabilities, patterns of likelihood. The universe was not a clock but a symphony, one that played with both order and improvisation. The constant also gave rise to a new vision of matter and light. It connected the two realms, proving that they are not separate forces but two expressions of the same energy. Later, when quantum field theory emerged, H was the thread that tied all interactions together. It even became essential to understanding the birth of the universe itself, appearing in equations that describe the first moments after the Big Bang, when the cosmos flickered into existence in bursts of quantum energy. Planck's constant became more than a number. It became a symbol of humility. It reminded scientists that even in their quest for certainty, the universe would always reserve a margin of mystery. No matter how precise the instruments, there would always be a scale too small, an interval too brief, a quantum boundary that could not be crossed. That limit was not a failure of knowledge. It was a reflection of how reality itself is built. Today, every technology that defines modern life owes its existence to H. Transistors, lasers, solar panels, GPS, quantum computers, all function because of the laws that Planck's constant revealed. In laboratories, it continues to define the standards of measurement. The kilogram itself, once tied to a physical artifact, is now defined by the value of H, the ultimate proof that this constant is no mere theory but a fundamental truth of nature. Looking back, one cannot help but see the poetic irony. The man who introduced H did not set out to change the world. He was simply trying to solve a stubborn problem. Yet his constant became the bridge between the known and the unknown, between the human mind and the cosmic code. It taught scientists that reality, in all its complexity, is both orderly and uncertain, both simple and profound. It taught humanity that even the smallest number can contain infinity. And so, in that single symbol, H, rests the key that unlocked modern physics. It opened the doors to the quantum age, redefined our understanding of energy, light, and matter, and forever changed the way we see the universe. It is the whisper at the heart of every photon, the rhythm of every atom, the boundary between what is possible and what is unknowable. Through it, Max Planck gave humanity not only a constant, but a new vision of creation itself, where even the tiniest action carries the pulse of eternity. The reluctant revolutionary, how Planck himself doubted his own findings, reveals one of the most deeply human sides of science. The birth of quantum theory was not a triumphant march, but a quiet conflict inside the mind of the man who created it. Max Planck did not see himself as a revolutionary. He did not want to destroy the old world of physics or replace its grand, continuous laws with strange new ones. He was, in truth, the opposite of the radical genius many imagine. He was careful, methodical, and profoundly respectful of tradition. Yet destiny chose him to be the one to open the door to an entirely new vision of reality. And that door opened not with pride, but with hesitation. After his 1900 discovery, Planck felt no joy, only unease. His equation worked perfectly. It explained the mystery of blackbody radiation that had haunted physicists for decades. But it did so by proposing something absurd in the eyes of the old world. That energy, the most fundamental essence of the universe, did not flow smoothly but came in jumps, in discrete packets. It was an idea that contradicted everything he had ever believed. Planck had been trained in the tradition of Newton, Maxwell, and Helmholtz, men who saw nature as continuous and predictable, ruled by laws that could be expressed with absolute certainty. His own instincts told him that reality must be uniform, without gaps or sudden leaps. Yet the data, the experiments, and the mathematics whispered otherwise. His formula was undeniable, but its meaning was unbearable. In the years that followed, Planck tried to reconcile his discovery with the old principles. He rechecked his equations, explored alternate explanations, and even tried to interpret his quanta as mere mathematical conveniences rather than physical entities. To him, they were scaffolding, temporary supports for a building that would later be completed with continuous laws. He did not see them as pieces of reality. He wrote privately that he had introduced the quantum against his will, as an act of desperation to make sense of the experimental data. He believed that once the mystery of radiation was fully understood, these quanta would disappear, replaced by smoother, more elegant equations. But nature refused to comply. Every new experiment confirmed what Planck's constant implied. Energy truly was quantized. Einstein's explanation of the photoelectric effect in 1905, based on Planck's work, showed that light itself behaved as if it were made of particles, photons. It was a revelation that Planck admired intellectually but resisted emotionally. He could not accept that the elegant waves of Maxwell's theory, which had unified electricity, magnetism, and light, were incomplete. In his heart, he remained a classical physicist trapped in a quantum world. As the years passed, other scientists began to take his reluctant idea and build upon it. Bohr applied it to the atom. Heisenberg and Schrödinger transformed it into the foundations of quantum mechanics. Each of them credited Planck as the father of the revolution. Yet Planck himself never fully embraced the title. He admired their brilliance but was cautious of their bold interpretations. The idea that uncertainty, probability, and discontinuity ruled a microscopic world was something he found difficult to accept. He once remarked that while the new theories were useful, they lacked the moral and philosophical satisfaction of the classical order. To Planck, physics was not just a profession, it was a moral pursuit, a way to uncover divine harmony. The thought that nature might be governed by chance rather than certainty troubled him deeply. In this inner conflict lies one of the most profound truths of scientific history, that even the greatest discoveries are often born in the hearts of those who fear them most. Planck's reluctance was not weakness, it was integrity. He did not celebrate the fall of the old laws because he revered them. He respected the stability they represented, the beauty of a universe guided by reason. But truth is not bound by comfort. The same discipline that made him cautious also made him honest. He could not ignore the evidence simply because it unsettled him. He faced his own disbelief and let the truth stand, even when it contradicted everything he hoped to preserve. This tension between faith and fact gave Planck a unique nobility. He embodied the humility that true science demands, the willingness to bow before reality, however strange it may be. He never sought fame, and he did not boast of revolution. Even after receiving the Nobel Prize in 1918, he downplayed the significance of his work, describing it as merely a new form of the old law. But by then, the world knew better. The reluctant revolutionary had already transformed human understanding. The constant he discovered had become the foundation of quantum mechanics, atomic theory, and modern technology. What makes Planck's story timeless is that it captures the emotional truth of discovery. Real breakthroughs are rarely moments of celebration. They are moments of confrontation between belief and evidence, between the known and the unknown. Planck stood in that fragile space, torn between the world he had grown to trust and the new one his own equations had revealed. He was not the destroyer of the old order, but its most faithful servant, forced by truth to admit that it could no longer stand. In the end, Planck came to accept, quietly and without fanfare, that the universe was far more mysterious than he had imagined. He acknowledged that discontinuity was not chaos but another form of order, one too deep for the human mind to comprehend fully. He saw in quantum theory not disorder, but the hidden pulse of creation, the subtle rhythm by which light, matter, and energy dance. He once said, "Science cannot solve the ultimate mystery of nature because we ourselves are part of that mystery." Those words reveal a man who had made peace with uncertainty, who had learned that even doubt could be sacred. The reluctant revolutionary never claimed to understand the full meaning of what he had discovered. But his doubt did not diminish his legacy. It deepened it. It showed that true genius is not the absence of uncertainty, but the courage to face it. Max Planck's hesitation was not weakness, it was wisdom. It was the stillness of a man standing before the infinite, aware that he had touched something eternal yet beyond comprehension. His reluctance reminds us that even the greatest discoveries begin with questions, not answers, and that sometimes the most powerful revolutions are carried not by those who seek to change the world, but by those who cannot ignore the truth when it reveals itself. The legacy of a quiet man who transformed how we understand light, matter, and energy is not the story of fame or glory, but of quiet greatness. Max Planck was not a man who sought attention. He did not crave the applause of discovery or the thrill of controversy. He was a scholar who believed that truth, once found, spoke for itself. Yet through his humility and persistence, he changed the very language of science. His ideas redefined the structure of the universe, the nature of energy, and the limits of human understanding. The man who once believed his work would end with him, instead ignited the flame that still lights every corner of modern physics. His legacy is not only written in the equations that bear his name, but in the very fabric of the reality we live in. When Planck discovered that energy comes in discrete packets, or quanta, he unknowingly laid the foundation for the entire scientific revolution of the 20th century. Every law of modern physics that followed, Einstein's theory of relativity, Bohr's model of the atom, Schrödinger's wave mechanics, and Heisenberg's uncertainty principle, rests upon that single idea. The constant he introduced, H, became the key to a universe once thought to be perfectly continuous but now revealed as finely grained, composed of individual pulses of energy. Light, once believed to be a smooth wave, became both wave and particle. Matter, once seen as solid, became dynamic, vibrating with invisible quantum rhythms. The barrier between substance and energy dissolved, replaced by the realization that everything, from the glow of a star to the breath of life, is woven from the same quantized thread. Planck's legacy was not built on the noise of revolution, but on the silence of precision. His work did not come from rebellion, but from discipline, from an unshakable faith in logic and patience. It was this faith that carried science beyond the boundaries of the visible world. Before him, physics could describe what was seen. After him, it could describe what was unseen. He transformed the laboratory into a window into the subatomic realm, where light and matter dance according to probabilities, not certainties. Every technological miracle of the modern age, lasers, semiconductors, atomic clocks, quantum computers, is an echo of Planck's insight. His equations became the tools with which humanity reshaped the planet. But Planck's influence goes beyond machines and theories. He transformed the way humans think about knowledge itself. Before him, scientists sought absolute truth, laws that could predict every movement of every object with perfect precision. After him, they learned to live with uncertainty. His discovery introduced humility into science, a recognition that there are limits to what can be known, and that even those limits are meaningful. The quantum world is a place of mystery, yet it is also a place of order, an order revealed through probabilities governed by patterns so subtle that only mathematics can describe them. Planck taught humanity that mystery and logic are not enemies but partners in the search for understanding. In his personal life, Planck remained the embodiment of simplicity. He loved music deeply, often saying that the harmony of physics reminded him of a well-composed symphony. His home was filled with pianos, not trophies. He taught with gentleness, guided by the belief that knowledge should serve truth, not ego. When his discovery began to reshape science, he never sought to lead a movement or claim credit. He quietly encouraged younger physicists, Einstein, Bohr, and others, to follow the path that his equations had opened. It was as if he had built a bridge, but chose to stand behind it, watching others cross into the new world of the quantum. Tragedy shadowed his later years. The world he had helped enlighten was darkened by war and loss. He endured the deaths of his children and the destruction of his homeland. Yet even in grief, his faith in reason and morality never faltered. He continued to teach, to write, and to speak of science as a sacred pursuit, not a weapon, but a way to glimpse the divine order beneath creation. For Planck, every discovery, no matter how small, was an act of reverence. He saw in the laws of nature a reflection of something eternal, something beyond human pride or ambition. Science, he once said, advances one funeral at a time. He knew that progress was not a single leap but a slow unfolding, a chain of truths carried by generations. His legacy lives not only in the equations, but in the example he left behind, the image of a scientist guided by conscience, humility, and perseverance. He taught that discovery is not born from arrogance, but from respect for the unknown. In an age when knowledge grows louder, Planck's silence speaks even more profoundly. It reminds us that the deepest revolutions do not come from noise but from clarity. Today, Planck's name marks constants, satellites, and research institutes. His ideas have traveled to the edge of space and into the depths of atoms. Yet his greatest monument is invisible, the quantum world itself, which hums according to the constant he discovered. Every flash of light, every atom's vibration, every burst of energy carries within it the rhythm of Planck's legacy. He changed how humanity perceives existence, no longer as a rigid machine but as a living, breathing universe, where even the smallest particle sings with meaning. In the end, Max Planck's life was a quiet revolution. He did not shout to be heard, he listened until nature spoke. He did not demand recognition, he sought truth. His constant, small, simple, eternal, became the language through which modern science speaks. The man who doubted his own discovery became the architect of a new cosmos. Through him, light, matter, and energy were revealed not as separate forces, but as one continuous song, a cosmic melody that begins with a single note, H, the heartbeat of the universe. How his ideas led to Einstein, Bohr, and the entire digital universe we live in today stands as the final movement in the great symphony that Max Planck began more than a century ago. What started as a quiet equation in a dimly lit Berlin laboratory grew into a chain of discoveries that reshaped not only science, but civilization itself. Planck's insight that energy exists in discrete packets, quanta, became the seed from which modern physics sprouted, branching out into the work of minds like Albert Einstein, Niels Bohr, Werner Heisenberg, and Erwin Schrödinger. His constant, H, became the pulse of the 20th century, a number so small that it seemed trivial, yet powerful enough to transform how humanity sees the universe and itself. The story of how Planck's ideas gave rise to Einstein's revolutions begins with light. In 1905, Einstein, then an unknown patent clerk, read Planck's papers and saw in them something that Planck himself could not yet accept. Planck had proposed that the exchange of energy between matter and radiation happened in quanta, but he still imagined light as a continuous wave. Einstein dared to take the next step. He declared that light itself was made of quanta, later called photons. With this idea, he explained the photoelectric effect, a phenomenon in which light striking metal surfaces ejects electrons in precise, measurable bursts. It was experimental proof that light was not just a wave but also a particle. That discovery, grounded in Planck's constant, won Einstein the Nobel Prize and confirmed that the quantum was real. Planck's reluctant equation had given birth to a revolution. Niels Bohr soon followed, using Planck's quantum to build the first accurate model of the atom. In his vision, electrons orbited the nucleus not in random paths but in fixed energy levels, quantized orbits. When an electron jumped from one orbit to another, it emitted or absorbed a quantum of light, the amount of energy determined by Planck's constant. For the first time, the mysterious spectra of light emitted by elements were explained not by guesswork, but by quantum law. Bohr's atom was a living demonstration of Planck's principle, a universe not of smooth motion but of leaps and transitions. From there, the quantum idea grew into an entirely new framework of thought. Heisenberg built on Planck's work to develop matrix mechanics, a mathematical structure that described how particles move not deterministically but probabilistically. Schrödinger complemented it with his wave equations, showing that particles behave like waves of possibility rather than points of certainty. Every one of these discoveries bore Planck's signature, for at their heart lay h, his constant, the bridge between energy and frequency, between the tangible and the invisible. What Planck began as a solution to a single problem became the foundation for understanding all problems of energy and matter. Einstein's theory of relativity, though born separately, found harmony with Planck's quantum idea. Both reveal that reality is not what it seems, that time, space, energy, and light obey laws that defy common sense. Einstein's work on photons and Planck's work on quanta together opened the door to the atomic age. The understanding of how energy is released in discrete packets led directly to the discovery of nuclear fission and fusion, the forces that power both stars and human technology. From the quantum came the ability to harness the atom, to light cities, to send probes across the solar system, and, tragically, to build weapons of unimaginable power. Planck's constant became the measure of humanity's reach into the fabric of the cosmos itself. Yet the most enduring legacy of Planck's ideas is not found in destruction, but in creation. In the digital universe that defines modern life, the very principle of quantization, that energy and information exist in discrete units, mirrors the way computers operate. Binary code, the language of ones and zeros, is a reflection of the quantum truth that nature itself is built in steps, not continuums. Each electronic device, from the smartphone in a pocket to the satellite orbiting Earth, relies on the behavior of electrons inside semiconductors, behavior explained entirely by quantum mechanics. Without Planck, there would be no transistors, no integrated circuits, no lasers, no fiber optics. Every pixel that glows on a screen, every bit of data that travels through a network, exists because of the rules discovered by a man who never intended to change the world. The thread of Planck's influence runs through every great scientific mind of the 20th century. Einstein extended his ideas to light and relativity, Bohr applied them to the atom, Heisenberg and Schrödinger gave them mathematical life, Dirac and Feynman pushed them into the realm of particles and fields, the quantum field theory that now governs our understanding of the universe, explaining how particles interact, how forces emerge, and how matter is created, still carries Planck's constant at its core. Even the theories that seek to unify quantum mechanics with gravity, like string theory, measure their equations through the same constant. It is the heartbeat of physics, the universal signature that reminds us that all of reality, no matter how vast, is built from the smallest acts of energy exchange. The impact of this quantum legacy has reached beyond science, reshaping philosophy, art, and even the human sense of existence. The certainty that once defined classical thought gave way to wonder and ambiguity. Artists painted reality as shifting and uncertain. Philosophers embraced the idea that perception shapes truth. The world had entered an age where the boundaries between imagination and observation blurred, an age of complexity and connection. In the 21st century, as humanity steps into the realm of quantum computing and artificial intelligence, it continues to walk the path that began with Planck's hesitant hand writing E equal to h nu, the digital universe, the invisible network of data, signals, and computation that surrounds and sustains modern life, is at its core a quantum creation. Every transistor operates because electrons obey Planck's rules. Every laser beam that reads information, every quantum sensor that measures distance or time, every MRI scanner that looks into the human body owes its existence to that constant. The future itself, quantum networks, teleportation of information, and quantum artificial intelligence, all trace their ancestry to Planck's discovery. The quiet man who once feared that his theory would be forgotten has become the architect of the most connected, advanced, and illuminated era in human history. And yet, beyond the machines and mathematics, the true legacy of Planck lies in what his work revealed about knowledge itself. It showed that truth is not always grand and obvious. Sometimes it hides in smallness, in a constant so tiny it seems meaningless until one realizes it governs everything. It taught that revolutions do not always roar. Some arrive on the tip of a pen, in an equation scribbled out of frustration, in the whisper of humility before the mysteries of the universe. Max Planck never saw the digital world his discovery would create. But every time light travels through a fiber optic cable, every time information leaps across space in a burst of data, every time an electron jumps in a microchip, his presence endures. The man who once called his idea an act of desperation unknowingly defined the architecture of modern reality, from the glow of a screen to the fusion of a star. From Einstein's photons to the quantum code that drives technology, all of it sings the same note, the note of H, the constant heartbeat of the cosmos, the echo of a quiet mind that transformed the universe forever.